Hello friends, I hope that you are doing great, learning some of the very basics of air pollution, then their sources, measurement techniques, instrumentations, and I hope that it is a good beginning for you, and I hope that you will be able to understand some, you will be able to get some idea about fundamentals of air pollution. So, as in the last lectures we were discussing about aerosol optical properties, and in this lecture we are going to discuss again the continuation of the same, because aerosol optical properties is one of the very important topics that needs to covered in the air pollution and atmospheric chemistry. Okay, so this is what you see. You have a particle and the part of the solar radiation, incoming solar radiation, here it is sunlight, and here it is considered as a monochromatic light. So, this means only we are for example, only monochromatic light 0.5 micron is given, and 0.5 micron is given because of some reasons we will see in this lecture. And you see here part of the radiations will be absorbed by this particle that we have here, and then a part of the radiation will be scattered. Okay, so you will get some scattered light here. Sorry for the typo, it is LIGST, and then we usually then you have some component of transmitted radiations or whatever the radiations that is going from here. So, basically you have I0, and because of this absorption and scattering, this light will be extincted. So, there will be extinction of light, and if you just add this both, we call it B extinction is equals to B absorption plus B scattering. Okay. So, this is what is happening, and when you do this, and this will be defined in the last lecture we have seen that I was given by I0 exponential minus B external into delta x r x. This was the relationship that we have seen. So, the intensity of the incoming radiation I and I0 incident radiation, and the radiation that is transmitted is actually like I. So, there will be a relation. So, if you see here some of the part of the radiation will be scattered actually, of course. So, some of the absorption and scattering we define as extinction, and when the absorption happens, this will lead to absorption will lead to transform to heat. The energy, sunlight energy that is there, electromagnetic radiation, when it is absorbed by molecule or gases or particles. In this case we are discussing about the particles. So, it is absorbing the radiation and it will be converted, the electromagnetic radiation will be converted in the form of heat, and that will be re-emitted when the temperatures becomes cooler. So, if you see I have here, yeah. So, and the scattering means redirects the energy to different directions. The energy will be redirected to different direction, but remember here the wavelength will remain the same. Okay, when in the scattering the wavelength of the incident radiation and scattered radiation, that will be same, that will not be affected. So, to sum up, aerosols can either scatter or absorb the electromagnetic radiation at different wavelengths. This is very important. This absorption and scattering is actually wavelength dependence. So, when we see when you measure the absorption or scattering or extinction, you have to mention that what wavelength you are doing. Okay. And then as I said that if you have absorption of light, it will be transformed into heat, and that can be re-released when atmosphere becomes cooler or surrounding becomes cooler. So, the particle will re-emit the radiation into the atmosphere. For example, this is the very important case for black carbon aerosols, and that is why black carbon is considered as a warming, actually warming agent along with CO2. So, this is very important thing that you have to remember, that this light absorption is released when atmosphere becomes cooler. Okay. And then you have the other component, scattering. We discussed actually scattering can be because of the particles, and it could be because of the molecules as well, gaseous molecules, but here we are mostly focusing because of the particles. So, here Rayleigh scattering, here the diameter of the particle or the radius of the particle is much smaller than wavelength of the incident radiations. So, usually for example, lambda is less than 0.03 micron, means less than 300 nanometer. Okay, so this particle, and this means it will be 300 micrometer. So, it will be 30, yeah, it will be 30 nanometer, right. If you convert micrometer into this one, so this will be 30 nanometer. So, you can see wavelength is actually the diameter is actually 10 order of 10 lower than the 290 or 300, you can just consider. And then if you consider the larger particle wavelength like 750, then it will be 25 times or so. So this is the very important thing, and this Rayleigh scattering is just, this means this Rayleigh scattering is because of the very fine particles or the gaseous molecules that are present in the atmosphere. And then Mie scattering becomes very important when the wavelength of the incident radiation is closer to the diameter of the particle. So, this is very important, and we have to consider this one. And we know that diameter of the particles, this means we are talking about here less than 0.03 micrometer will lead to Rayleigh scattering. So, the diameter has to be between 0.03 to less than 10 micrometer, and this will lead to the Mie scattering. And then when we say extinction is means sum of the scattering and absorption coefficient. So, just remember these things. So, aerosol particles can scatter and absorb the solar radiation, solar and infrared of course, and thus they can alter the air temperature. This is very important. So, when they absorb the radiation, what they will do, they will actually re-release the temperature, and then this can actually, this could either lead to the cooling or warming. Generally we talk about the particles which absorb the solar radiation, so they will have mostly warming, but you have aerosols, some of the aerosols which are actually cooling like sulfate and scattering actually aerosols. So, some of the aerosols which are actually more scattering and very less absorbing, they will be leading to cooling. So, the ultimate effect of whether the atmosphere will be cooling or heating will be dependent on what is the ratio of absorbing to scattering kind of aerosols, and that we will see that is defined as a single scattering albedo. And not only that, they can also change the rate of photochemical reactions. So, this is very important thing. Okay. So, this is again just see. So, you have actually two cases, that here extinction could be because of the gas and particle both. So, and then if you write extinction could be because of the B could be because of the gas or because of the particle, and then B extinction can be also written because of the absorption by the molecular particles and then scattering by the molecules or the particles. Okay. And then when you have absorption by the gaseous molecules, this will follow the Beer-Lambert's law. I gave the examples of ozone absorption. We discussed about 310 nanometer and one at 290 nanometer, and we saw the difference in the absorption that is there actually. Okay. So, this is very important process in the atmosphere. So, absorption by the gaseous molecules is also very important, and then we have scattering by the gaseous molecule, and that scattering by the gaseous molecule is called Rayleigh scattering. We discussed in the previous ones. And then you have actually absorption by the particles. Absorption by the particles generally is less than 10% of the extinction. So, it's some sort of kind of indication that our atmosphere is highly scattering, and suppose if you have domination of more of absorbing nature of particles, then the atmosphere will be more warmer. And then you have B scattering by the particles, that is called by that is usually called my scattering. So you have scattering by two, like gaseous and particles. So gaseous is actually Rayleigh scattering, mostly the gaseous absorbing molecules are scattering molecules, and then you have scattering by the particles is generally called as my scattering, and this becomes prominent when the wavelength and the diameter of the particles are comparable in size. Okay, so just remember this is very important. And the ultimate limit to visibility in a very clean atmosphere is Rayleigh scattering. Okay, because in that case what will happen, you have mostly the scattering because of the, so when we say ultimate limit to visibility or the maximum visibility that we can see is a very clean atmosphere where you have mostly the gaseous molecules, you do not have particles in the atmosphere. That is how you do not see the scattering by the particles. So you do not see the scattering by the particles, so you can further see it further long distance or very long distance, but my scattering usually dominates. Okay, so there are two cases in ultimate limit where we defined I0, if you just remember I upon I0, we defined actually is 0.02 kind of things. In this case it is mostly dominated by the Rayleigh scattering particles, we have very less aerosols in that one. And then the range of scattering by the particles about 10 to the power minus 5 meter inverse to 10 to the power minus 3 meter inverse. And one more thing is here to remember, usually 10 to the power 6 minus 6 meter inverse, this is written as 1 capital mm inverse. So you remember here when I say m means here m is usually million, so 10 to the power 6 and meter. Do not be confused here that million 10 to the, it is actually 10 to the power 6 meter inverse. This is not equals to 10 to the power 6 meter inverse. Okay, because you see some people get confused because m stands for million and million is 10 to the power 6 and meter inverse is meter inverse, but here in this case the way units are represented, it is 10 to the power 6 meter and inverse of whole of the thing. So you will have 10 to the power minus 6 and then you have meter inverse, and this is actually called 1 mm inverse. This is the standard unit that we used actually for extinction and absorption. So this is very commonly used, so you just remember this one. So if you just see this one, this means this will be 10 mm inverse to 1000 mm inverse. This is how it is actually. So scattering can vary from 10 to the 10 to 1000, so like million meter inverse. We will discuss aerosol optical depth in a separate section, but since we have actually it is a measure of extinction caused by scattering and absorption. So you have here like extinction. So extinction is actually like I wrote the equation I0 is equals to exponential minus B extinction, okay, into x. So sometimes x is written as delta x, so just do not be confused actually, or sometimes it is written as dz or sometimes written as z. So these are the unit of measure length, and when you see since B extinction has a unit of meter inverse and this is the has a unit of meter, this will lead to actually unitless. So when you see we define tau is actually B external into x, or you can just put that integration of B external B extinction, which is a function of height dz, and z is varying from 0 to z. So this you can actually remember, and that is how the aerosol optical depth is defined. In a column of thickness of z, you consider that how much radiation, solar radiation is attenuated because of the particles, okay, and then gaseous. Coming back to this again, if you just see this equation, sometimes as I said, if you just remember, this is in the previous one we discussed, this is B extinction and this is L is actually x. So do not be confused, several times it is written by different terminologies, okay. And then if you see B extinction is actually I prefer to write V extinction is proportional to the geometrical area, okay, of the particle that is there, and then it is also proportional to the number of the particles. If you have more number of scattering particles, V extinction will be higher, and then there it will be. So, this when you see this one, you can write V extinction is equals to some proportionality constant, and for example, you see Q E, A and N. Here sometimes you write area of the particle. So, AP means area of the particles. QE is becomes very important, and that is what is actually a kind of extinction efficiency. Okay. And this equation, by the way, is valid for monodispersed aerosol. So, this extinction efficiency is radiant power that is scattered and absorbed by a particle divided by the radiant power geometrically incident on the particle. So, if you see the geometrical area here, and so if you see here, and if you just remember the units here, because area will have unit of meter in square, number is actually number density. So, you have a particles per meter cube. Okay. So, this will give rise to unit of meter inverse. So, Q extinction is again a property that is actually unitless. Okay. So, what does the QE means? QE means it represents the relative availability of the particles to remove light from a beam compared with blocking or interception by a projected area of the particle. So, how much it means it is a relative quantity, that how much particle will be the light will be removed by the particles, and when you compare with this the when you have the consider its geometrical area or projected area. So, this does not have to approach 1. Usually QE value lies between 0 and 5. This is very important. Okay. QE values are usually, we will see some of the equations here. Okay. And again, since QE is actually extinction, so it can be actually defined extinction efficiency because of the absorption, and then extinction efficiency because of the scattering. So, these are the two equations that are there actually. So, if you just remember these equations, in this equation, if you see what area is actually, if you have diameter of particle dp, so AP can be written as pi dp by 2 to square. So, this will be pi dp square divided by 4, and this means that the sigma E RB extinction can be written as pi, okay, n number of particles dp square and QE divided by 4. This is actually the extinction coefficient because of the monodispersed particles. So, this is extinction coefficient due to monodispersed particle. Monodispersed means you have same diameter is not changing. So, if you just put this equation, similarly you can just put here this equations same V extinction, and in the form of L you can write here. Just remember here that area is the particle area, either you take in the centimeter square or you take in the meter square. If you are taking centimeter, then it will be centimeter inverse extinction coefficient. If you are taking meter, then meter square, then it will be meter inverse. Extinction coefficient efficiency, I said that is unitless, and n is the particle concentration. So, whether you can have particles per centimeter cube or particle per meter cube. So, you can define these things, and this is how this equation can be calculated. You can calculate the same concentration by the particles, in terms of, you have to just use the density of the particles here. So, this is the density. Okay. So, you just put the density and you can calculate this particle again, because you have to rho into V, and V is actually 4 by 3 pi r. So, r means d by 2. So, d cube by 6. okay. This is V, and then you have rho, and then 4 you have actually like 3 here, yeah, 4 by 3 pi, it will not be 6, it will be d to the power, this will be 8 actually, okay. So you, because d by 2 to the power 3, so it will be 8, 4 2 ja 8, and this will be actually 2 into 3 is 1 by 6, so by pi dp cube n rho divided by 6. So this will be your concentration, and this you can write in microgram per cubic meter or microgram per centimeter cube, or whatever way it is writing. And if you just put this equation, this same thing you can convert in the previous equations. So you can derive this relationship between I0 and I. So you can just do the calculation at home. Now this is the equation, okay. So this means you have been given that in this, for example in this one, the light attenuation is actually by 50%. So I upon I0 is actually 50, okay. Diameter of the particle is 0.7 micrometer, you remember. So in this case, and we are talking about the particles which is having the similar wavelength at the diameter of the particle. So source of the light is actually similar wavelength. So this means it will be, we are talking about the Mie scattering. And then L becomes 2 kilometer, for example L path length, and then L is equals to 2 kilometers, means you can write actually 2000 meter, and then QE is given is 2. For example, I discussed in the previous equation that this can be between 0, QE can be between 0 and 5. So we have to calculate what is the number of particles per meter cube, and if you remember this equation, what you have to do, you have to just put these equations here, okay. And by the way, this equations is little bit complicated, so just be careful, because there is exponential unit and there is actually a negative sign on this one. So the when you take ln I0 upon I, so it will be actually you have a natural log of 0.5 from this side, will be equals to, okay, exponential you can remove, and this will be equals to minus n dp square pi dp square upon 4 into QE into L, and ln you just see that what will be this number. I don't remember this how much number will be there, but anyway actually you can calculate this, and yeah. So if you calculate this number, and you have dp is given, QE is given, L is given, so there is only one unknown here, and you can calculate this number. So just to be careful with this one, because ln 0.5 will be less than, it will be negative values. So this negative value, this will be actually negative value, and this negative and this negative will be cancelled out. So the calculation will be in the correct way. So you can very easily calculate how much actually the extinction is because of the particles, or the given extinction is caused by the how many number of particles. Similarly, you can calculate the diameter. This is very important slide. As we discussed that, I did not discuss anyway. Yeah. So this is actually kind of mass and scattering, light scattering and absorption per unit mass. This is very important. This is another very important parameter. And this, if it is actually light scattering, then this is called mass scattering efficiency, and when we talk about the absorption, it is called actually mass absorption efficiency, and this is because of the per unit mass of the particle. So the unit will be micrometer square per gram. So just remember this one. This is very important, because if you know the MAE and the way these are actually related, V extinction or V absorption is equals to, because you have meter concentration, if you have just concentration, which is actually microgram per meter cube into meter square per gram. So if you just see this one, if you have just concentration of the particles, and if you know this one, you can calculate. So V absorption is actually, you can write that summation of concentration of ith species into the MAE of the ith species. Okay, you just put it, and I is actually like 1 to from say 3 or 4 species. Similarly, if it is case of the scattering, you can put this one here. This will be actually changed by MSE. So you have mass scattering. The important point is here, if you see here, absorption efficiency or mass absorption efficiency is relatively flat, except in the visible region you have some variations, but the scattering efficiency is very important. And see here cutoff values, okay, somewhere around, remember this one, so it is 10 to the power 0, it is the number is written is 10 to the power, so this means actually this is 1, so this means 0.5, this is actually 0.2, and 10 to the power minus 1 0.1. So you see somewhere around particles of diameter say between, it is 0.2, so somewhere say 0.1, more than 0.1, and then it is 1 or 1.5, here you have 2. So this becomes very important. Sorry, not 2, yeah, it is actually 2 here. And then if you say the peak of the absorbed scattering is actually somewhere around, peaking somewhere around here, about 0.5 micrometer. So the maximum, sorry, so the maximum are the highest value of scattering efficiency is about 0.5 micrometer. So this is where, if you remember in the previous lectures I discussed that most of the time values are high. We have taken here 0.5, you could have taken any value, but 0.5 is generally taken because the scattering is maximum at the 0.5, whereas the absorption is relatively flat when you talk about the diameter of the particles. So this becomes very important for us, and so this means particles effectively scatter and absorb both the radiation. However, mass absorption efficiency and mass scattering efficiencies are very different for different species. The scattering efficiency per aerosol mass is highest at about 0.5 micrometer, and that's why most of the time we report the values, for example, such as AOD, single scattering albedo, these values are reported at 0.5 because this maximum is there actually. So this is sort of like, we talk about the representativeness, this is a representative one. And MAE is relatively flat for aerosols, and this is why when we say that you have a particles of 10 microgram of fine particles, okay, so this is the mass of fine particles, diameter is between 0.2 to 1 micrometer. This will scatter over 10 times more than the 10 micrometer of coarse particle or particle of diameter more than 2.5. This is the reason actually that the maximum absorption is because of the, you remember that absorption is dependent on the wavelength, scattering is dependent on the wavelength. One way also to calculate, I discussed this one, B extinction, you can calculate summation of concentration of the ith species and mass scattering efficiencies of the particles. So as I said, this is the unit of meter square per gram, and you have microgram per meter cube here. So this, if you just calculate this, this will be unit of meter inverse, and this is why in the when we say reconstruction, when we reconstruct extinction based on the chemical composition, we usually use this equation. So 1 upon m is actually like meter inverse, nothing different, just another way of representation. Remember, this is very important. This extinction is a function of relative humidity, and if you see here in the atmosphere, most of the time you have ammonia, like ammonia will be converted to the ammonium ions. So this will be like NH4 plus, you have nitrate ions and you have sulfate ions. These ions usually they will exist in the atmosphere either in the form of ammonium nitrate or they will exist in the form of ammonium sulfate generally. and if you see here, these are actually depends on the relative humidity. So this, because there will be actually, these are water soluble molecules, water soluble species. So this will be actually kind of, they will have hygroscopic growth. You will see hygroscopic growth of the particles, and to account for that hygroscopic particles, we used function of RH. And 3 is the mass scattering efficiency. This is actually taken, although these values for, if you can calculate for nitrate and sulfate and ammonium individually, but since they exist in the forms of their salt, it is usually calculated like this, and 3 is taken as the mass scattering efficiency. The mass scattering efficiency for the organic carbon is taken as 4. So because of the organic carbon, and then this is light absorbing carbon, which we usually talk about, for example, black carbon. It has the highest mass absorption efficiency. Okay, so it is 10. And then you have sort of soil. Soil has a very small absorption efficiency. You can put it here, but the mass absorption efficiency for the soil you can calculate. And then you have a coarse mode particles. The mass scattering efficiency is taken here as 0.6. So based on this one, you can reconstruct. Otherwise, there is a instruments that is called a nephelometer. It measures the scattering coefficients. Okay, and this nephelometer works on the principle like we discussed in the previous one. This is the principle. This is the set of kind of things for nephelometer. Okay, so it measures the extinction, and then you can calculate the extinction based on this one. So I hope that I have given a fair idea about the scattering efficiency, absorption efficiency, and then their relation with the mass or the concentration that is there, and how you can construct with the, when the concentration of the particles is given, then you can calculate that one. I also discussed the mass scattering efficiency, which is peaking around 0.5 micrometer, and that is one of the reason why most of the time we report the optical properties as 550 or 500 nanometer or 0.5 micrometers. In contrast, absorption efficiency as mass absorption efficiency is relatively constant, and black carbon has the highest mass absorption efficiency, which is actually 7.5 to 10. It varies a lot, so there is no number actually, but you can just remember 7.5 plus minus 2, or so you can cover these numbers. So with this one, I thank you here, and we will meet in the next lecture. We will further discuss about the other optical properties. So thank you.